can influence some of the recommendations and some of the do's and don'ts. So we'll talk a little bit about that, and then a lot of the meat of the presentation is going to be provided by Howard Kemp. And Howard just has just a wealth of experience in all different types of applications, and with successful deployments around the world. So, we'll get into cable etiquette around blowing and pulling, and then I'll pick back up at the end talking a little bit more about aerial installations. But before we get into the depth around cable and cable etiquette, just something that you wanted to highlight is that the fiber is the network. And so, the glass fiber is ultimately what carries the signal. So that is the network. And really what the cable is there to protect the fiber. And we think that it's very important never to lose sight of that, because sometimes we'll talk with people and they get very focused on, on different cable parameters. But we always need to come back to the fact that, the fiber really is the network, and the cable's there basically to to protect it. So over the last few years, we've seen different types of fibers, different types of fiber structures. So we've got different fiber diameters. There are loose tube and micro cable designs. There are flat ribbons. There are rollable ribbons. And then there are also two main cable structures. And really what I wanted to focus on in this slide primarily were the cable structures. There's the central tube structure, and there are stranded structures. And, just the reason to go through these is that just given the inherent properties of each one of these designs and the various makeups, they sometimes, just require different treatment and different do's and don'ts when we're dealing with them in the field. And so we'll talk about that a little bit more as we get into the depth of the presentation. But it's very, very important to recognize the type of product that you're working with, and just make sure that you've got appropriate recommendations for that specific product type. So as a starting point, standards are always a very good starting point, but we consider that compliance to standards really is a starting point. It doesn't ensure success. But just wanted to highlight some of the common fiber standards and some of the common cable standards. So Telcordia, there are various ITU fiber recommendations. And for a lot of what we see in the outside plant today, I'd say the big majority is G.652 and or G.657 are the primary versions. When we get into some of the very high capacity networks, we are seeing some more 654 and a little bit of 655 there. And so those are some common fiber standards. Some common cable standards are the ANSI ICEA standards, as well as Telcordia GR20. And then for those people who are deploying all dielectric self-supporting cables, the IEEE has a different standard, and that's IEEE 1222, which is a standard predominantly focused on ADSS cables. There are different types of, a few different additional types of cables that are out there that are a little bit less, less common. But with, what you saw on the last slide, as well as these standards, this covers probably, 80 to 90% of what we see in the outside plant today. Just one other note is some very high, fiber density cables are less standardized. So, certainly over the last decade, we've seen, many different generations of micro cables, and also the advent of rollable ribbon cables. And these are a little bit less standardized in comparison to some of the other, the other products. And so you want to make sure, again, that you understand the products that you're working with, and make sure that you are applying the appropriate installation recommendations and do's and don'ts to the proper cable. So some limitations, and so these are some fundamental limitations that drive, just these do's and don'ts. And one of the first one, certainly is tension. And with fiber, it is, I think, reasonably well known now that diameter fiber is stronger than steel. And certainly, when designed and installed properly, fiber can last for decades, and we have seen that. So we're at the point now with, commercial deployments of fiber into its fourth and fifth decades. And so, we have seen that fibers can last for decades, and really the quality of what we are deploying now, is much better than the quality that was deployed in the first, couple of decades of life. And so, also we have a little bit deeper understanding. So, we expect that we'll continue to see very long lives for fiber networks. So something that is also very important is that the coating of a fiber is an integral part of fiber strength performance. And when you get down to the actual performance of the fiber, the glass strength is very important, and the intrinsic strength of glass is roughly 600 to 800 kpsi. And give a range there because it depends on how you measure and the parameters according to measurement. But something that's very important is if there are flaws that are either caused in the manufacturing process or caused by deployment in the field, then those flaws can limit the strength of the glass, and ultimately that will limit the strength of your network. And there are people, so I've got fiber strength in one slide, and there are people that have given multiple decades and devoted their careers to really understanding the intricate details around what happens with fibers under strain and in various situations. And the knowledge that those people have brought to us as an industry has been just invaluable, enabling us to really have the reliability that we have today. And that reliability can be somewhat summed up in we limit fiber strain to less than 0.2% of the proof test level of the fiber long term and 0.6% short term. And what that does is it limits any potential growth of the flaws or growth of cracks in the fiber, and that has been a real key to the long-term reliability that we've seen in the networks that have been deployed for these past decades. So to illustrate, when you look at the fiber and fiber purity and flaws, so I mentioned flaws can decrease the strength of glass, but one of the questions is, okay, really how pure is this glass, and how much do I really need to worry about these flaws? And I put just a picture of a Georgia Powerball ticket on the screen, and the reason for this is that the raw material impurities are measured in literally parts per billion. And so the glass that we use in manufacturing the fiber that goes into today's communications networks is absolutely ultra pure. And so, when you look at that from a rough standpoint, you are roughly 3 times more likely to win Powerball than you are to find impurities in the fiber core. And so that helps to illustrate, you put together just the fact that, we understand how the flaws behave. We also, start out with intrinsically just a very pure product and a very clean product, and that helps to contribute to the reliability that we have today. So from here, what I'd like to do is that's a little bit of background on what goes into fiber strength, and I'm going to turn it over to Howard for a little bit of practical understanding regarding how you can treat your cables for strength properly. Over to you, Howard.
Okay, thank you, Mark, and thank you all in the audience for joining us today. We do appreciate your time. So Mark had mentioned earlier that there's a couple of cable standards that basically define the properties of the cables, in particular GR20 and the ANSI ICEA specification. And they specify a lot of different mechanical properties, optical properties that's required of the cable. And in particular, what I want to talk about right now is that they both require a maximum rated cable tension of 600 pounds for the cable. Mark also mentioned that for short-term loads, that we have to limit the fiber strain to 0.6%. So as a cable manufacturer, it's our responsibility to design a cable that meets both of those parameters. As an installer, it's the installer's responsibility to ensure that the cable is installed without exceeding that 600-pound maximum rated cable load. So, and the most common way that we do that is by using a capstan winch. And the capstan winch is a very popular tool that's used to install cables. What's key to the capstan winch is that you have to match the capacity of the capstan to the maximum rated cable load of the cable that you're installing. So very important. Everybody in the audience probably has seen this equipment and recognizes that requirement. There are sometimes a few people that haven't seen the rule. And maybe, you know, they're installing a cable, the cable gets stuck, and they're tempted to pull the cable with a backhoe, a truck, or some other powered equipment. Please never do this. That equipment is not designed to install fiber optic cable, and it can certainly overtension the cable, as you can see in this upper right-hand picture, where some unfortunate installer actually broke the cable in half by using a truck or a backhoe or some other equipment to install the cable. But it's more than just that. You can exceed the rated cable load without breaking the cable. And when you do so, you can damage or reduce the long-term reliability of the fiber. So just because you may have gotten away with overtensioning the cable doesn't mean that you haven't damaged the cable. So again, please never use this powered equipment when you're installing the fiber cable. This is another common procedure that I see pretty frequently in the field. And this is where an installation crew is using a powered take-up reel to pull the cable. Again, this is not recommended. The reasons being is that there's no tension limitation with this type of equipment. This line truck can certainly apply much higher load than 600 pounds to the cable. Another reason we don't recommend this equipment is because the fiber is wound under tension, and it stays under tension. It stays under tension until the cable is removed from the reel. So it can see that high tension for long periods of time. So we may exceed our short-term reliability time periods. And finally, when you're pulling cable with a powered take-up reel, when you're pulling cable under tension, very difficult to level wind the cable. So what happens is the cable ends up piling up on top of one another. You get a very poor level wind. You get cable wraps that are crisscrossing over one another and creating macro bends in the cable, also creating high compressive forces in the cable, which may potentially damage the fibers inside the structure. We do recommend that you use a breakaway swivel. The breakaway swivel is designed to break at a 600-pound tension, so that it's really sort of like wearing a belt and suspenders, but it is a cheap, inexpensive tool to guarantee that you don't overtension the cable. We don't necessarily recommend that these devices be used in aerial installations unless you use a safety sling between the pulling eye and the pulling rope in the event that the breakaway swivel does fail, and that way the safety sling would prevent the cable from falling to the ground. I'm often asked the question, what's the biggest cable? What's the largest cable that I can pull into a given duct? And typically, we recommend that the diameter ratio, and the diameter ratio we're defining as the cable OD divided by the interduct ID, be less than 75%. And in general, you're going to have a pretty good, successful installation if you maintain a diameter ratio below 75%. Of course, there's always people who want to put, the highest fiber count. They only have one duct in the ground, and they need to get as many fibers into that pipe as possible. So yeah, there are occasions where people are going to exceed that 75% diameter ratio. However, just be aware that it may lead to difficult installations, particularly if the duct is crushed, if it's full of silt, if it's in poor condition. So if you are going to use these high diameter ratios, we do recommend that you proof the duct beforehand, just to make sure that you won't run into those problems during cable installation. If you're designing a long haul network, I recommend that you stick with 75% or lower. You just don't want to be dealing with the difficult installations on a day-to-day basis when you're installing a long haul network. And at this point, I'm going to turn it back over to Mark, and he's going to talk a little bit about some fiber bending parameters.
And so if you've seen any of our other webinars, one of the slides that we show on a pretty regular basis, because it is just absolutely critical to just to the properties of the fiber and to successful network deployment, is just respecting the bending properties of fiber. So this graph shows bending loss versus wavelength and what happens when you bend a standard single mode fiber more tightly. So you can see the blue line is a 10 millimeter radius, the magenta line is 7.5, and then get down to 5 millimeter radius. And you can see that the loss increases significantly. So just in general, some trends that we've seen overall in networks is networks are going to longer and longer wavelengths, and then we also see cables being deployed in tighter and tighter bends, and so we just have to be very cognizant of that. So as we see bending occurring, there are different signatures that we can see, and this is actually interesting just from a field troubleshooting standpoint. So there are some bend loss signatures that can compare, or that can contrast macro bending versus micro bending. And so the intent isn't to get into depth as far as what those are, kind of assuming that that the audience knows some of the differences there. But if you compare versus the baseline micro bending, if you see micro bending in cables, then you often see an elevated loss throughout the wavelength range, with a little bit of increase in the 1500 nanometer wavelength band. But with macro bending, and macro bending is where the bending, the cables and the fibers are just bent way too tightly, you can see that loss increases, pretty dramatically. So, from here, bending is, a very important thing that we are focused on, just making sure that we, treat properly. I'm going to turn it back over to Howard to talk about, just how we manage that.
Okay, thank you, Mark. So again, as a cable manufacturer, it's our responsibility to provide bending recommendations for the installers in order to protect not only the fiber, but also to protect the structure of the cable itself. So typically, we specify a minimum bend radius, and minimum bend radius is typically specified as a multiple of the cable diameter. So looking on the right-hand side at the red circle, for example, minimum bend radius with load is 20 times the OD of the cable. And remember that typically in a data sheet, and not only for OFS, but I think for pretty much most all manufacturers, that the data sheet is going to talk about bend radius. So when we go to select the fiber optic cable sheave or the capstan, we have to multiply that radius by 2 to determine the diameter required for the installation tools. Minimum bend radius is specified for different applications. You see here that OFS does specify a minimum bend radius for cable coiling, as well as during installation and after installation. After installation being once the installation load has been released from the cable and the cable tension is at 0. And also I want to point out that typically different multipliers may be used for different cable designs. For example, we may use a multiplier of 10x for a small loose tube cable. For a small ribbon cable, that multiplier may be 15x. So just be aware that there are different multipliers for different cable designs. So again, it's always best to refer back to the data sheet just to confirm what the requirement is for the cable that's being installed. So how do we control bend diameter? Well, we do that by using the correct diameter capstans, as shown there on the right. We also control bend diameter by using correct diameter fiber optic cable sheaves and quadrant blocks, as shown on the bottom right photo. And again, we also control bend diameter or bend radius by forming cable storage loops in the correct diameter. And it's important to recognize that not controlling the bend diameter may result in fibers being crushed due to the installation process. And we'll see more on that as we go on. So just as a general rule of thumb, when you're selecting your capstan diameter, typically, and again, I always ask people to refer back to the data sheets, but typically for low fiber count cables, and I'm defining that as up to 216 fibers, a 30-inch diameter capstan is going to be suitable for most cables. If you get up above 216 fibers, be aware that larger capstans, maybe a 40-inch, may be required. For ultra-high fiber count cables, 3456, 6912 fiber cables, even larger capstans, maybe a 50-inch diameter may be required for the application. Guiding the cable in and out of handholds and manholes. So do use proper shivs and quadrants. Do use fiber optic cable shivs. An example here shown on the right of a fiber optic cable shiv. This particular shiv is manufactured by Conducts, has a large diameter, suitable to support the bend radius for the cable. And on the left, showing a large diameter quadrant block, also designed for fiber optic cable, that is suitable, maybe not for all cables, but is suitable in some applications. And again, I'm going to touch on that right here in this next slide. So in particular for OFS cables, we allow the use of fiber optic quadrants on central core cables. However, we do not allow their use on loose tube cables. The reason being is that the central core cables generally provide a higher compressive strength for the on the cable. It provides better protection for the fibers when the cable is pulled over these small rollers. Now again, it's a fiber optic cable quadrant that has to be used. I'm going to show some examples in a couple of slides here of tools that should not be used for that application. This is a common technique where inner duct is used as a feed tube to guide the cable in or out of the handhole or manhole. And this is acceptable as long as the inner duct is strong enough, stiff enough to support the minimum bend radius. If you see that the inner duct is deforming, or if it's the bend radius, it's forming a tight bend radius, you need to stop the installation and figure out a different way to install the cable. And here's a couple examples of tools not to use. The upper left chimney shiv, the two-wheeled block there, not recommended for fiber optic cable. It's not designed for fiber optic cable. There's only two wheels. The wheels are undersized. It doesn't provide enough support for the bend radius. The lip roller shown on the upper right photograph, again, not recommended for fiber optic cable. Those tools are used for ropes, pulling wire rope, steel rope, maybe pulling copper cable, but are not intended for, nor are they recommended for use on fiber optic cable. And again, the fiber optic quadrant, which is shown on the lower left photo there, has multiple rollers. The rollers are spaced closely together to provide adequate support to the cable. And the major radius of the quadrant is large enough to support the minimum bend radius for the cable. If there's one slide that I would like the audience to remember at the end of the day, this is the slide right here. Rollers that are too small or the wrong type are the most frequent cause of cable installation damage. And that's worth repeating. Rollers that are too small or the wrong type are the most frequent cause of cable installation damage. Generally what happens, small diameter wheel, high tension, high sidewall pressure, high compressive load on the cable can damage the internal components of the cable. You might not even see it on the jacket of the cable. The jacket of the cable may not show the damage, but when you test the cable, surprise, you have broken fibers. And here on the right, this is an example of just a case like that, where a customer had broken fibers. We located the position of the broken fibers. We dissected the cable, autopsied the cable at the location of the broken fibers. You look closely at the photographs, you can see that the rows and the aqua tubes are very flat. They've been crushed. You can also see this was an armored cable. You can also see little crosshatch marks on the buffer tubes. Those are actually indentations that were caused by the corrugations of the armor layer. So there was enough compressive force on this particular cable that the armor corrugations indented the buffer tubes. And then you can see the broken fiber. Broken fiber is indicated by the helium neon laser light that's leaking out of the broken fiber there. So again, small rollers or the wrong type, most frequent cause of cable installation damage. Please, you spend a lot of time on your installation equipment, you spend a lot of time on labor, take the time, acquire the correct tools, use the proper fiber optic cable shears, fiber optic quadrant blocks to protect the minimum bend radius. Storage coils. I mentioned that OFS does recommend minimum coil diameters for storage coils. You may find that not all manufacturers provide this recommendation in their data sheets. But again, confirm with the data sheet the requirements. And again, remember that the radius is going to be specified in the data sheet. In order to determine the diameter of that cable storage loop, the diameter is 2 times the radius. So here's just a photograph of a nice looking storage coil in a handhole. Nice large diameter, nice generous radius. This photograph's a little bit dark, but let me just explain what's going on here. So this is a small fiber to the home pedestal. The the inside dimension of the pedestal was about 7 inches. And the installer actually stored cable loops inside that pedestal. So the diameter of the storage loops was at most 7 inches. Typically, this cable probably requires about a 12-inch storage diameter. So we could see that potentially, at the apex of that radius, the cable's probably being deformed. It's probably putting compressive load on the buffer tubes or the central core tube. I don't know what type of cable this is, but definitely this is an application that is not recommended. I think 2 things happened here. One that in general, cables should not be stored inside these small pedestals. So the installer obviously was not aware of that recommendation. And secondly, he obviously wasn't aware of the minimum bend radius for storage coil application. So a couple of mistakes were made here. Again, please refer to the data sheets to determine minimum storage coil diameters. Just a couple words about storage methods, cable storage methods. This is a method that we refer to as the fold-over method. Sometimes it's called the twist and fold or the crossover method. Works pretty well for small diameter cables. You basically you lay the cable out into a large bite, cross the legs over as shown in step 2, and then flip the coil over and repeat until you get the storage coil down into the handhole or the manhole. Again, this method works well for small small diameter cables because you have to fit the coil down into the collar of the manhole. So it's going to be limited to where your storage coil is maybe 28 to 30 inches diameter maximum. One nice advantage of this storage method is it typically you can eliminate most of the twist from the storage coil. So that is always a good thing if you can eliminate the twist. Next storage method we call the teardrop method. Again, lay the cable out in a large bite, form a small teardrop at the end, and start rolling the cable, form the cable into this yin-yang symbol shown in step 4, and just keep rolling the cable until you get it into position in the manhole or the handhole. Again, this method is suitable for small diameter cables because the storage coil has to fit down through the opening of the manhole. And the last method here is the garden hose method. And it is just as it sounds. Basically, the cable is just stored and coiled like you would coil your garden hose. This really is the only option available for large diameter cables because the storage coils may be too large to fit down through the opening of the manhole. So basically you just form the coils one coil at a time, tape them down, strap them down, and repeat until all the cable has been stored. This method does introduce twist into the storage coil. So it's important that you maintain the proper diameter for the storage coil. Figure eights. Figure eights generally are pretty benign. Just a couple of words on figure eights. We do recommend that you spread out the crossover points of the figure eight. Also, if you're figure eighting a long length of cable, figure eight the cable in 2 piles or 3 piles. Don't make one huge pile. Spread the cable out. And finally, in the bottom picture, you note that the cable is stored on a tarp. If you're in a muddy area, it's a good idea to use a tarp to keep the cable from picking up mud and debris, which will only make your installation more difficult. And also, if you're in an area where there's brush or other other twigs or sticks or whatever that may snag the cable, possibly kink the cable, it's always a good idea to lay a tarp down just to protect the cable. Figure eight stacks should be limited to no more than 2 feet in height. And that basically is to limit the weight of all that cable on the bottom layers. So if you see you're getting up to about a 2-foot height, it's time to start your second figure eight. And last slide on figure eights. I've seen crews make very neat figure eight stacks. They were very proud of them and they look very pretty. Unfortunately, all the crossover points were stacked up directly right on top of one another. And what happens is that all that weight has to be carried by the bottom layers of cable. And so you end up getting very high loads, very high compressive loads on the bottom layers of cable. And you can see in this particular circumstance that all the weight of those upper layers of cable actually, the compressive load was so high that it actually deformed the cable. So you want to avoid making a pretty figure eight stack. It's always better just to spread the stack out and spread out that load. Okay, I'm going to move on to blowing. Blowing is actually the preferred installation method. A blown installation, in contrast to a pulling installation, uses distributed installation forces. So you can avoid the high concentrated force that's applied to the cable when you're pulling the cable. So results in a low stress environment for the cable. And also it allows for long continuous installation lengths compared to pulling the cable. Blowing is not impacted as much by bends in the duct as pulling is. Bends have a very, very severe impact on your pulling lengths when you're pulling cable. But there is an impact in blowing, but not nearly as severe. Do follow the manufacturer recommendations for pressures. That's both for air pressure in the duct as well as the drive pressures, whether it be air pressure or hydraulic pressure on the drive track or the drive wheels. But also in addition to that, it's always good to conduct slip tests and buckling tests using the cable just to ensure that you don't over push the cable, possibly slipping the tracks on the cable or buckling the cable. We're going to see some photos of that in the next slide. And again, this is what can potentially happen if you apply too much pressure to the drive tracks or to the drive wheels. The top right photograph shows that the cable jacket has been abraded, has been worn away because the tracks were slipping on the cable. So what happened in this case was that the cable slowed down or the cable stalled, but there was enough hydraulic pressure applied to the tracks. The tracks continued to spin and damage the cable. On the lower left, we can see where the cable has been buckled. Again, what has happened is that the cable has slowed down, perhaps has stalled. The drive motor of the blowing machine is continuing to push the cable and actually pushes hard enough to actually buckle the cable inside the inner duct. one last example on the upper right. This is another example where the cable was buckled inside the interduct. So if you see that happen, if the cable stalls, or if the drive wheels or the drive tracks are slipping on the cable, you want to stop the installation immediately to avoid that type of damage. And I think this is my last slide. This is the diameter ratio for cable blowing. You see that we recommend a range of diameter ratio here. And again, it's the same ratio that we spoke of before. It's the cable OD divided by the duct inside diameter. We're recommending a range of 50% to 75% for ideal conditions. We do recommend a lower limit of 50% because if the cable gets too small inside the duct, there's just a better chance, higher probability that you could potentially buckle the cable inside the pipe. So 50 to 75% is the optimal range for diameter ratio for blowing installations. Just want to note that sometimes micro cables, they'll push that limit a little bit higher. The micro cables being smaller diameter, smaller weight, doesn't take quite the same airflow to install the cable. So you can get by with a little smaller clearance between the cable and the interduct. So you may see slightly higher recommendations for micro cable applications. And at this point, I'm going to turn it back over to Mark, and I'm going to speak a little bit about aerial installations.
Yep. So we will close the rest of the session out talking a little bit about aerial cables. I really like this this picture because typically we see a couple of different types of aerial cables, either fiber optic cables that are lashed to a messenger or to a strand, or all dielectric self-supporting cables. And actually, you look at this picture, and there's a little bit of both on this pole. But just a little bit about aerial lashed networks and some cable etiquette. So cables lashed to messengers have some span length limits correlating to NESC loading district. And so just one of the things to highlight is, even though there is a messenger and a fiber optic cable, we just also need to make sure that we are keeping the applied load on those fibers less than the 0.2% long-term strain. And so there are some limits on what you can do with typical fiber optic cables when they are lashed. And so the limits are needed to reduce the fiber strain under storm load, as well as just limit the tension of the suspension strand. And there's one additional thing to highlight is that additional cables, as you add additional cables to a messenger, that is going to increase the weight. It's also going to increase the overall bundle of cables when you put ice on them, and that's also going to increase the amount of strain that whole system sees in wintertime. And so, with that, we would very much, and different manufacturers may have different recommendations, and so we'd recommend to contact your manufacturer, and we have some recommendations that we've placed on the screen, but contact manufacturers for specific recommendations. And all dielectric self-supporting cables, they have different tensile properties than standard lashed cables or underground cables, and these cables are typically designed, they see their lowest tensions during installation, and they are designed to withstand, the tensions of either ice and wind, or both long term. So they typically have higher applied loads, and you very much would want you to consult your manufacturer for stringing, sag, and tension information. And a lot of times manufacturers will provide sag and tension documents that relate the sag of the cable for a certain span to the tension, and also how that looks with different loading conditions. And when you're doing ADSS installations, we very much would recommend using a dynamometer or other tension measuring methods to measure the stringing tension. There are different ways that you can actually measure the tension, measure the sag of a cable, and would very much recommend that people installing ADSS use that. So with ADSS, as Howard mentioned also, cable crushing is the largest cause of installation damage with ADSS as well. And stringing block size is critical for ADSS installations, and very much do follow manufacturer recommendations for stringing blocks. Another another thing to focus on with ADSS is twisting. And so, do use pulling swivels to reduce twisting during the ADSS installations. But again, as Howard mentioned, not breakaway swivels. We don't want cables to break when they're being deployed and fall, and fall onto a road or into traffic. So, don't recommend the use of breakaway swivels. Do avoid excessive twisting by tying the string block up at the appropriate angle. And actually, you can see an example of that in this upper picture. And another thing, and you can see it in the lower picture, is to monitor twisting with a flag. And you can also just be aware of print string corkscrew. So if you start to see the print string getting deformed, or you see just what looks like just a tremendous amount of twisting during not beyond normal twisting, then you certainly need to stop the pull and reset the pulling those stringing blocks. And so in summary, know your cable, the appropriate standards, the tensile, bending, and compressive properties. And first of all, that's the most important thing. So once you know what you're working with and what it can do, then you just make sure that it's not a hard thing. Just avoid excessive bending, twisting, crushing, and tension. And as Howard provided just a number of different tips for pulled, blown, and then aerial cables, and then just overall, when in doubt, absolutely seek out guidance. And so, that is the end of the presentation. We are absolutely happy to take some questions from here. And I know that we've had a few come in already, but thank you to Janice and Amy for the opportunity.
You're very, very welcome. Thank you guys for a great presentation. Lots of good information. And Howard, I loved your comment about, do not pull those things. You're going to break them. It's so true. The instinct is to want to do that type of action, but not good to do with this industry. So we have questions here. Let's start with how long will my network last if I install it correctly? I think you guys covered this a smidge, which I'm glad to hear that they have some lifeline there, but if you can go into more detail, that would be great.
Yeah, so I'll consider this one to be a gimme. I'll take this one, and the reason it's a gimme is because we've basically already done it. If the cable is installed correctly, we have every reason to believe that it's going to last for several decades or longer. The fiber itself, if we're not putting too much strain on the fiber, then there's no reason to believe that the fiber is going to spontaneously break. We've seen that play out again and again and again, where fibers and cables have lasted for decades. In fact, there's kind of a pretty famous experience throughout the industry where tornadoes can come through and hurricanes can come through, and everything's fine with the telecommunications network until somebody goes out and cuts the cable. So so we have every expectation that the cables are designed properly for the network and deployed with installation recommendations is going to last for multiple decades.
That's great. That's really nice to hear. Okay, wonderful. What are some practical cable pulling and blowing limits or distances between handholds? That be a Howard question?
Yeah, Janice, I'll take that one. So it varies widely, and it depends on the application and the network that the handhole and conduit structures are designed and intended for. I've been on long haul installations where the conduit and handholds were designed and constructed with that in mind. And blowing distances, 2,000, 2,500 feet, day in, day out, no problems, even longer in some cases. So, in that case, handholds were spaced. Typically, they're spaced maybe about every 1,500 feet or so, just in case they needed access to the cable. But they would typically join the pipe together and blow the cable 3,000 feet. However, in fiber to the home networks, where there's a lot of curvature in the conduit, and the ducts sweep up from the horizontal and sweep up vertically into the bottom of the handhole. And there's handholes, basically on every corner, every 300 feet apart or something like that. And you have to use loops of interduct to join the conduit together. Blowing distances are going to be very restricted. All of that geometry is really going to restrict your maximum blowing lengths, maybe to 1,000 feet, 1,500 feet. And likewise for pulling. Long haul situations, early on before blowing became popular, I've been on installations where the conduit was designed to install a kilometer length of pulled cable. You don't see that very often anymore. So I would not recommend that anybody plan to pull a kilometer of cable. Again, maybe 1,000 feet between handholds on a long haul install. And again, if you're in an urban area, fiber to the home type project, 500 feet, might be pushing your limit. And again, it all depends on the geometry of the duct, how the ducts enter the handhole, and that sort of thing. So the correct answer is it depends on the geometry, but the practical answer is for blowing anyways, good conduit, 2,500, 3,000 feet. For pulling distances, good conduit, 1,000 to 1,500 feet.
Great. Thank you. I love having your experience here on this webinar. Thank you so much, Howard. That's great. This relates a little to the conversation a bit here. How do I slip? How do I do slip and bucketing tests when setting up a blow cables? There we go.
Okay, I'll take that one also. Typically, the manufacturer, the blowing equipment manufacturer is going to provide procedures for doing this. But just in a quick summary, on a slip test, and these tests are destructive, so you need to conduct the test on a short piece of cable. You only need about 20 or 25 feet of cable and interduct, but the tests are destructive, so make sure that you have the excess cable available. Slip test, basically what you do is you tie one end of the cable down so it can't move. So tie it to the bottom of a tree, the bottom of a telephone pole, tie it to the bumper of a truck. Put the other end of the cable into the blowing machine. You don't need air. Put it into the blowing machine. Clamp down on the rollers or on the drive track, and slowly start increasing the hydraulic pressure or the air pressure on the drive track until the tracks actually begin to slip on the cable. So that determines the maximum drive pressure or maximum pressure that can be applied to the tracks or the wheels without slipping. So during installation, you don't want to exceed that value. Now, I want to point out if you're using more than one blowing machine, at the second blowing machine, the cable is going to have some residual lubricant on it. So you want to conduct a test in that case that has a residual layer of lubricant on it, because it's going to slip quicker in that case than it would on a dry cable. The buckling test is conducted again, and this is also a destructive test. You need about a 20-foot section of interduct. Fold over the far end of the interduct, feed the cable into the machine, into the blowing machine. Again, you don't need air. This is all for the hydraulic pressure on the drive wheels and the drive track. Push the cable into the far end of the interduct where it's folded over, and so that the cable comes to a stop. Hopefully the cable will stop and the drive wheels will stop also. What you want to do is you want to repeat that test, keep repeating that test, and each time apply a higher hydraulic pressure or a higher air pressure to the drive tracks until instead of stopping, the cable either continues pushing into the interduct and buckles inside the interduct, or maybe it might buckle inside the air chamber of the blowing machine proper. So again, it's kind of a short explanation, but that's how the tests are conducted. And again, always you can refer back to the equipment manufacturer for more detailed instructions.
Okay, thank you so much, Howard. Here's actually a question about something you might manufacture. They're asking, does OFS make or plan to manufacture air core fiber that has a velocity factor very close to 1:1?
Yeah, so I'll take that one. That's actually a very, very interesting question. It's a little bit out of the scope of what we were talking about today. But what I would say is if you would contact me, we call that hollow core fiber. And we actually had a press release about it a little bit earlier this year. And so if you'd like to contact me, I can certainly put you in touch with the people who were involved with that product line.
Okay, perfect. Thanks, Mark. And Mark's email is right here on this slide, so you can reach out to him that way. All right. Are you going to, actually this might have been already covered, are you going to reference spec for static BR and pulling BR?
Yeah, I'll take that, Janice. Yeah, we again, OFS has 3 recommendations for bending radius. One is during installation while the cable is under load. The second is after installation, after the load has been removed from the cable. And that would apply more to like if you're racking cable through a manhole or racking cable on an equipment frame or something like that. And the third one for bending radius was the storage coil diameter. So yes, we have 3 recommendations for 3 different applications.
Thank you very much. Let's see here. Someone would like to know what your stance is on flexible microduct.
So I'll take a first pass at that, and then Howard, if you want to add anything onto it, I think in general, we consider ducts of all types to be very good things. They help with installation of cables, and so what we would say, we just would want to make sure that the recommendations that Howard had laid out in terms of ratio, diameter ratios and those kinds of things are followed, and make sure that the bends are properly managed. But I think we like ducts of all different types. And I'll turn it over to Howard to see if he has anything else he'd like to add.
Yeah, I guess I'm just a little bit puzzled by the word flexible, but yes, we do recommend for our microcables. Our microcables are designed to be blown into microduct. So we like to see the cables used only in blown applications. They do have a limited tensile strength, and they can be pulled for short distances. For example, if you have to get the cable into the basement of a building or something like that. We don't recommend, in general, pulling long lengths of the microcable because it's just not designed for that application. So yes, we do recommend microduct be used with our microcable. Again, I'm not sure what the word flexible means. Maybe it means individual microducts rather than microducts that are bundled together. I think if the microducts are bundled together, it probably provides maybe a little better protection against compressive loads. If you're installing microducts into an interduct, then really the only choice is to install individual microducts into the interduct. So hopefully I answered the question. If not, please resubmit.
Okay, thank you so much. So I see it's already 2:06. I can't believe I went by so quickly. We're going to keep going. We've got 1, 2, 3, 4 more questions, but if you need to sign off, participants, go ahead and come back and go to our website, and you can click on this to get the recording. You'll already be registered. So with that, I'm going to continue on, guys, if you're willing to stick around with me, gentlemen, which I know you are. So here's another question. When adding to an existing pole line, this is actually kind of I'll be interested to hear your answer. When you're working with an existing pole line, would all existing service providers have to be notified and approve the sizing and type of cable that can be placed? I know that's a pole.
Yeah, so
What do they
yeah,
call that?
I'll take a first.
Yeah, you want to take
Yeah,
that,
I'll
Mark?
take a first pop at that one. Yeah, I'll take a first
Okay.
pop at that one. And really, we do the manufacturing of the products. We are not familiar with all the regulations in all of the different areas. So the one thing that we would say is we want to make sure that um, the the service provider is looking at the just overall the capabilities of the poles that are in the network, as well as the the strand that's in the network, and just making sure that all that stuff is within limits. So I'm going to give a very non-committal answer to that one, and just making sure that that uh, the combinations of poles and loads on the poles, as well as the loads on the strand, and all that are properly taken into account, and that typically happens without having to contact all service providers. But again, that's one of those that I think is that I'm going to give somewhat of a non-committal answer, and I think that's probably the best we can do there.
Yeah, I'll just add.
The pole loading.
Yeah, my recommendation would be you probably don't need to notify everybody, but you certainly need to notify the owner of the pole line, because they're going to be very interested in what types of structures are on their pole lines, and what effect does the added weight and tension have on my pole line. So by all means, please notify the owners.
Yeah, years ago we did a webinar on that type of technology that's available for that type of question, and for the life of me, my brain is not connecting with it right now, so I apologize. But there are some definite details that go into it, and some companies that even can help with that. So thank you, gentlemen, for covering that for us, even though it's not directly related to your specialty. We appreciate the insight. Let me see here. Okay, this is good. Some slides show two fibers being installed simultaneously using a capstan. Does OFS recommend this practice since the cables can cross each other on that capstan?
Yeah, and I'll take
Howard?
that one. Yeah, I'll take that one. Can you hear me now? So.
Oh, yep, we can hear you. Sorry.
Yeah,
Go
okay,
ahead.
okay. I lost track of my mute button there. Yeah, so yeah, thank you for picking up on that. That's a very keen observation on that photo. I thought I would slip that photograph in there without anybody noticing, but yes, it did show two cables being pulled over the capstan. That particular customer was very interested in pulling two cables at the same time into the same duct for this particular application. And I just want to say that the trial was very successful. We did not have any problem with the cables twisting over one another as they went over the capstan. Did not have that problem whatsoever. Typically, the cables were the exact same design, and I think that was helpful in keeping the cables side by side. If you had cables that were different designs, one large diameter and one smaller diameter, I think the two cables may behave differently. So yes, for two cables of the same size, same diameter, same design, I think you're safe to pull two at the same time.
Great. That's really cool that you did that with them. Good, like you said, a trial. That's really nice to go outside of the norm for that client. All right, last question. Any guidance on overblowing, quote unquote, overblowing?
Yeah, I'll take that one also. Yes, we've had some successful installs where a customer has an occupied interduct and needs to get a second cable along the cable route, and that's the only space available. So yes, we have had successful installations. Typically, what we recommend is that you use a micro cable for that application, and you first install a microduct. You can install the microduct in short lengths, couple it together in your handholes or manholes. Once you have all your microduct installed and coupled, now you can come back and you can blow a long continuous length of cable into that occupied interduct. You can do it with standard outside plant cables, but you're going to be limited. Sometimes it's difficult to couple the interduct in that case, so you're limited. You can only blow the cable from one handhole to the next. So it's a very laborious installation process. So our first recommendation, again, would be install the microduct first, come back later and blow the long length of microcable.
Wonderful. Thank you so much, Howard. All right, everybody, you've got Mark's email there.